Since Pi Day is coming up, I thought it would be a good time to make some videos about pi. But I thought pi probably deserves more than one day. So throughout this month I'm going to be making videos related to pi. Some of it will be on the history of pi. Some will be geometry related to pi. Infinite series, integrals, number theory, lots of different surprising appearances of pi. But I think a good place to start would be with Archimedes. So the ancient mathematicians already studied circles to some degree, and they knew that pi was around 3, a little bit more than 3. But of course that's not a great approximation. One way to show right away that it's going to be bigger than 3 is to take a circle and a regular hexagon inside it. So let's say the circle has radius 1, just to keep things simple. Then the perimeter of the hexagon will be 6, because we have 6 equilateral triangles, so each side length is also 1. So the perimeter is 6, and that's going to be less than the perimeter of the circle, the circumference of the circle, which will be 2 pi. So that immediately tells you that pi is bigger than 3. Okay, now if you're a serious mathematician, you probably want to have a better estimate than that. So what Archimedes did is he took this one step further, or actually several steps further, and around 250 BC he got the estimate that pi is between 3 and 1/7, or you could write 10 over 70, and 3 and 10 over 71. So he basically got it within an interval of length about 1 over 500. So this will at least give you 3.14. I won't tell you what the digit after that is, but the digit after is at most 2, so it gives you a much better estimate than 3. So the way Archimedes got this estimate was to do this method with the hexagon, but just take it to the extreme and do it with 96 sides instead. So once you have 6 sides, it's pretty easy to cut them each in half and instead do a 12-sided polygon. Okay, so that gives you a better estimate. And then you can do 24 sides. Well, it's already getting hard to draw because it's getting close to the circle already. And then you split it in half again and again. So you go from 6 to 12 to 24 to 48 to 96. So each time you double the number of sides, and since the ancient Greeks were pretty good at geometry, they could handle cutting angles in half without too much difficulty. So I'm going to show what expression you get for pi with the 96 gone. Of course, Archimedes wouldn't have written it in this form because he didn't have the same notation, and also Greeks did not like square roots. One unfortunate drawback of this method is that it gives a ton of square roots nested to make things even worse. So let's see what we get. So if we start with the 6-gon, aka a hexagon, we have an angle of 60 degrees, but I think I'll use radians, just because, well, for one thing, it involves more pi's, but also it allows you to see the limiting process a bit more easily. So this would be an angle of pi over 3. Now we can drop an altitude. Now we have a right triangle with hypotenuse 1, so this side length here is sine pi over 6. And then to get the perimeter, well, we have to double it to get one side and then multiply that by 6. So we have 12 sine pi over 6. Okay, so if we do this over and over until we get to a 96 gon, we'll get 192 sine pi over 96. And if you know properties of the sine function, you know that sine of a small angle is roughly that angle, so sure enough this should give you a number pretty close to 2 pi. So we can get an exact answer using half-angle formulas from trigonometry. Of course, the Greeks didn't really have that, but what they were doing when they were approximating pi is essentially half-angle formulas. So if you have an angle theta, then sine theta over 2 is root 1 minus cosine of the angle all over 2. Okay, so if we start with theta equals pi over 6, we'll get sine pi over 12 equals root 1 minus, okay, now cosine of pi over 6 is root 3 over 2. Okay, so that's a bit of a mess, but you can simplify it to root 2 minus root 3 over 2. And then the cosine of that angle will be the same thing, but with a plus sign. Then you cut it in half again, and what you end up with is, well, something even messier. It's 1 minus root 2 plus root 3 over 2, all that over 2. And then that simplifies to root 2 minus root 2 plus root 3 all over 2. Okay, and we keep going. Now if we cut the angle in half 2 more times, what we'll end up with is 192 sine pi over 96, 192 times root 2 minus root 2 plus root 2 plus root 2 plus root 3 all over 2. Okay, so every time you cut the angle in half, you have one extra 2 in that section. So this is certainly something that, if you wrote it in this way, would have terrified the Greeks, but nonetheless, they didn't really have any issues approximating it. So finally, we get 96 root 2 minus root 2 plus root 2 plus root 2 plus root 3. Okay, and of course we could carry on doing this as long as we want, but it gets more and more annoying to estimate these square roots. So in the limit, we'll get exactly 2 pi, but that's not very efficient for calculating pi. However, about nearly 2,000 years later, this same kind of expression came up in the very first infinite product for pi, which is 2 over pi equals root 2 over 2 times root 2 plus root 2 over 2 times root 2 plus root 2 plus root 2 over 2, and so on. Now, that again is basically trigonometry with half-angle formulas over and over again. This was found by Vieta in the 1500s. And he actually used it to compute quite a few digits of pi. Now, I won't get into this right now because there's still a lot of history in between Archimedes and Vieta, but we will get to this soon, and then we'll see that once the 1500s come along, there's a huge advancement in not just formulas for pi, but also efficiency at computing pi.